Okay, so today let's learn how to draw electron dot diagrams or Lewis dot structures of ionic compounds. So before we do this, you have to know about the periodic table and why it's set up that way. You also have to know about atomic structure. So if you don't know these topics, please refer to my earlier videos so that you'll know how to do these electron dot diagrams. So before we start, again, looking at the periodic table here, it is set up also because of the number of valence electrons in a certain atom of an element. So what are valence electrons? So valence electrons is the number of electrons in the outermost shell of an atom of an element. So these are the number of electrons in the outermost shell or subshell of an atom of a particular element. So depending on the type of element, you'll have different numbers of electrons. So for example, if you look at the first row, the alkali metals here, these are the alkali metals. These are the alkali metals, so they will have a 1 electron in their outermost shell. So for sodium, it has 1 valence electron. Hydrogen also has 1 valence electron. So that means in the alkali metals, all these elements here in this first column have 1 valence electron. And this is the electron that will actually either be removed from the atom to interact with another molecule, or another element. So looking at the group 2 metals, these guys here in this column, these have 2 valence electrons that can do chemistry. Now looking at the p subshell, the elements here that have electrons in the p orbital. So here in this column, these elements here have 3 valence electrons. I think you know where this is going. The column here, they have 4 valence electrons. And the next column with nitrogen has 5 valence electrons. The oxygen column has 6 valence electrons. The halogens have 7 valence electrons. And the noble gases have 8 valence electrons. So next we shall see how the number of valence electrons is a huge type of data that we need to draw electron dot structures. Okay, so here we have, I've chosen a little bit of atoms, and let's do some electron dot structure on these simple atoms, whether they're ions or neutral atoms. Okay, first one is rubidium. So as you can see, rubidium is in the group 1 metal. Here's rubidium. So we know that rubidium has 1 valence electron, so we simply put that. So that is the electron dot diagram of rubidium. If we want to look at rubidium plus 1, we have to remove an electron. So rubidium plus 1 electron dot diagram is simply just this, rubidium. And since it's a plus 1 charge, you can go like this. Okay? So this is the electron dot diagram, and rubidium plus 1 is this electron dot diagram. If we look at fluorine, fluorine is over in halogens. So in the halogens, all these guys here, these have 7 valence electrons. So fluorine Fluorine's electron dot diagram will look like this. 7 valence electrons around a fluorine atom. If we want to do fluorine minus, we add an electron, because now there is a net negative charge, as opposed to 7 protons, there is now 9 protons and now 10 electrons, and 7 of the 10 electrons are in the outermost shell. Sorry, 8 of the 10 electrons are now in the outermost shell of fluorine minus. So this is fluorine minus's electron dot diagram. Now what about the transition metals? These guys in the middle with that have d orbitals and f orbitals. But copper there is in its electron configuration, copper has 3d. Actually, it's a 3d 10-4s1. So electron configuration copper, again, you may want to refer to an earlier video on electron configuration, but at this point you really don't have to know about that. What I can say basically is that for the transition metals have at least 2 valence electrons. Some have more than 2, but at least 2 valence electrons in its outermost shell. So, again, you can look at copper. That would be copper. And copper plus 1 is just removing one electron, so this is now copper plus 1. And copper plus 2 is just simply that. You're removing another electron. Again, you don't have to know about electron configuration just yet, but it is helpful when looking at the transition metals. I will have a video on electron configuration, so that will help you out in figuring this all out. Okay, so now we're going to do electron dot diagrams of ionic compounds. So here I have 3 ionic compounds: calcium chloride, magnesium oxide, and iron-free chloride. Okay, for the first one, calcium chloride. So again, the valence electrons that calcium has, since it is in the group 2 metal, or the alkaline earth metals, calcium is going to have 2 valence electrons. And then chloride, each chlorine atom is going to have 7 valence electrons. So you can see we need 2 chlorine atoms so that we're going to satisfy the octet rule when it comes to the chlorine atoms. So as you know, calcium is a metal. So calcium is a metal. And chlorines are nonmetals. These are nonmetals. And nonmetals accept electrons. And metals donate electrons. Usually. So that means that when calcium and chlorine get together, they will transfer the electrons from the metal to the non-metal. So this will go there, and that electron here will go to this chlorine. So therefore, that's how you will write your answer to the teacher, but the final form is this way. So calcium now, because it donated 2 electrons, is now going to have a +2 charge because it gave 2 negative charges away. And now the chlorine, each chlorine will have now that electron from calcium, and I'll just put that one in red. And since the chlorine atom gained an electron, each one will have a -1 charge. So then this is your final answer here. That is the electron dot diagram of calcium chloride. Now moving on to magnesium oxide. So magnesium again is in the group 2 metal, an alkaline earth metal. Again, 2 valence electrons for magnesium. And oxygen is going to have 6 valence electrons. 2. So in this case, magnesium, which is the metal again, is going to donate its electrons to oxygen, which is a non-metal. So we just need one oxygen to take both electrons from magnesium. So our answer then becomes magnesium then will be a 2+ charge because it gave away 2 electrons. And the oxygen is going to gain 2 electrons. Since it gained 2 electrons, it gained 2 negative charges, so it will be a 2-. So then this is your final answer for the electron dot diagram of magnesium oxide. Okay, so for iron 3 chloride, as I said before, the transition metals have at least 2 valence electrons. In this case, iron has to have 3 valence electrons. Each chlorine will have 7 valence electrons. And the iron, being the metal, is going to give away its electrons to the non-metal, which is chlorine, in this way. So our answer is going to be, since iron gave away 3 valence electrons, it becomes a 3+ charge, and each chlorine now will have an extra electron from the iron. And since each chlorine has accepted 1 electron, it is going to have, each one will have a -1 charge. So this is your answer for the electron dot diagram for iron 3 chloride. Okay, now I've picked out some ionic compounds, but the anion is a polyatomic anion. So polyatomic anions are actually covalently bonded types of entities. So I will show that in a second. So let's look at sodium hydroxide first, okay? So we know that sodium, let's figure out, make sure you understand it, sodium is going to have a +1 charge. And we have to also know that hydroxide has a -1. So you have to know these designations before you do these kinds of problems. Again, sodium is in the group 1 metal, so it's going to want to give away an electron, and it's actually going to give away an electron to the hydroxide entity, okay? So let's do the Lewis structure of hydroxide, because hydroxide is a covalent compound. Or a covalent ion, all right? Okay, so let's practice Lewis structures. Okay, so oxygen, 6 valence electrons. Hydrogen has 1. That's 7 electrons plus the negative charge. So +1, that means 8 electrons we have to show in our Lewis structure for hydroxide. Okay, so we have to show 8 valence electrons. So here is our skeletal structure first. So we had 8 valence electrons to start with. We used up 2 because of the bond between oxygen and hydrogen, so we have 6 left. So we're going to add obviously 6 electrons to the oxygen because hydrogen cannot have more than 2 electrons around it. So we're going to add all 6 to the oxygen. Okay? So at this point then we are finished, because then this is your hydroxide Lewis structure. Okay, so that now that we know that that negative charge here came from the sodium, so here is our sodium. So that is actually the electron dot structure of sodium hydroxide. Okay, so let's do now barium sulfate. So again, barium is going to have a 2+ charge when it's in an ionic compound, and SO4, which is a sulfite ion, is going to have a 2-. So again, these 2 electrons came from the donation of the barium to the SO4. Okay, so let's take a look at the Lewis structure of SO4 2-. So sulfur has 6 valence electrons, oxygen has 6 valence electrons. There are 4 oxygens, so it's 24 plus 6, that's 30, plus the 2 electrons that are coming from the barium, that's 32 electrons we have to have for the SO4 2- anion. So the next step is write out the simple skeletal structure. Sulfur in the middle. And by doing this simple skeletal structure, we used up 8 electrons. So 32 minus 8. So 32 minus 8 is 24 electrons. We're going to add 24 electrons going from the outside atoms first. Okay, so are we done with this Lewis structure for SO4 2-? No, we are not. Even though we have satisfied the octet rule with sulfur and oxygen, the problem is formal charges, which a lot of students forget. Formal charges. Okay, so to figure out formal charges, again, sulfur has 6 valence electrons, each oxygen has 6 valence electrons. As drawn in this diagram above here, how many atoms is sulfur contributing to this diagram? Well, it's contributing 1, 2, 3, 4 electrons. So sulfur has a +2 charge here. How about oxygen? Well, each oxygen is contributing 1, 2, 3, 4, 5, 6, 7. So each oxygen has a -1 charge. So as drawn, sulfur here has a +2 charge, and each of these oxygens have a -1 charge. Well, this is very unstable, because nature would like to have the sulfur, the central atom, to have a 0 charge. So to do that, we have to form some double bonds. Again, we cannot add any more electrons. We have to make donating electrons from the oxygen. So let's donate this pair lone pair electrons from here, and let's get another one from another one here to make this structure. Okay, so now we have this structure. Now let's check the formal charge on sulfur. So sulfur, as drawn, is contributing how many electrons? Well, 1, 2, 3, 4, 5, 6. That makes the sulfur charge to be 0. And then now we have 2 types of oxygens. Okay, let's do the single bonded oxygens, call them oxygen A, and the ones with double bonds, we'll call them oxygen B. So for each oxygen A, it's contributing 7 electrons, as drawn, 1, 2, 3, 4, 5, 6, 7. So those have a -1 charge. And the oxygens that have a double bond are contributing 1, 2, 3, 4, 5, 6. So they have a 0 charge. So this is fine. So this oxygen here has a -1 charge. This oxygen has a -1 charge, which is fine because overall this entity has a -2 charge, as written here. So that is the Lewis structure for the sulfate anion, SO4 2-. So all we need to do is, we know that barium gave away its 2 electrons to the sulfate, so it has a +2 charge. So this then is the electron dot structure for barium sulfate. Okay, so the next one is aluminum phosphate. So aluminum has 3 valence electrons, which it will give away to a phosphate. So when it gives away its electrons to the phosphate, aluminum will then become an aluminum plus 3, and phosphate, by gaining those 3 electrons, will be phosphate 3 minus. But again, let us draw now the electron dot structure for aluminum phosphate. Okay, so phosphorus has 5 valence electrons. Oxygen has 6. So this is 24 plus 5, 29, plus the 3 electrons from the aluminum. That makes this 32 electrons total that we have to show in the Lewis structure for PO4 3 minus. So phosphate's in the middle. So by doing this, we use up 8 electrons. So we remove them from 32, and that gives us 24 electrons. So we add them to the oxygens. So then, are we done now? No, we are not. Again, the octet rule has been followed. That is good, but the formal charges don't work out. Again, the formal charge on that phosphorus is what? So it's phosphorus with its 5 valence electrons, but as drawn, it's only contributing 4 electrons. So it's contributing 1, 2, 3, 4 electrons to the drawing. So this phosphorus has a +1 charge. And each of the oxygens as drawn is a 6 minus 7. So each oxygen is a -1 charge. So again, it's because the phosphorus is not a 0 charge that we have to do something about this. So to do that, we just have to take a lone pair from one of the oxygens and form a double bond with the phosphorus. Like so. So now this phosphorus is contributing 1, 2, 3, 4, 5 electrons as in the drawing. So 5 minus 5 is equal to 0. So now that we have the central atom to be 0, then this is going to be the final Lewis structure for PO4 3 minus. So again, this is the Lewis structure for phosphate. So 3 minus is here. And all we need to do is show the aluminum gave away its 3 electrons, so it has a +3 charge. So now this is the electron dot diagram of aluminum phosphate.